All right, last topic in the chapter, relative velocity, relative acceleration, relative position. This deals with what happens when you have two different reference frames, one of them moving relative to the other. So we'll imagine is we have some reference frame A that is stationary, and then moving within that reference frame, we'll have a second one. Let's see, x prime, y prime versus x and y. We'll label this one reference frame B, and we'll say that reference frame B is moving at a particular speed. We'll talk about the speed of reference frame B and reference frame A. Or velocity for that matter. This could be a two-dimensional thing, so I really should make it a vector. This is the velocity of B measured in A. Now here's an example of exactly this kind of thing. Imagine you're got someplace like airport. You see these pretty frequently at airports. And there's a moving sidewalk. It's kind of like an escalator, but it just goes horizontally along the surface. That escalator, or actually an escalator would, but that moving sidewalk is like reference frame B. It is moving relative to you, standing still in reference frame A. So the stationary reference frame A and the moving reference frame, the moving sidewalk. All right, where things get interesting is when we have a particle and the two observers are trying to talk about the location of the particle. So in B, they'd be saying that this particle is located at a point that depends on x prime and y prime. So it would be at x prime, y prime. In reference frame A, they'd be looking at the particle and saying, well, sort of. In fact, its actual location depends on x and y. So they would have a different coordinate system describing their location. What we want to talk about is what would the position be measured in particular reference frame. So let's say we want to find the position of object P in reference frame A. Well, in order to find its location, we'll have to think about how reference frame B has moved. Its motion will be VBA times the time, and that'll tell you how this reference frame has moved. So initially, maybe they start out at the same location, but over time, B moves away from A. All right, then the location will be whatever reference frame B says it is. So this is the location of P in reference frame B, plus the location of reference frame B in reference frame A. So this is location of frame B in frame A. All right. So this is a classic equation in physics. This is called, I hope I spell this right. Give me a sec. It's spelled with an I. Galilean transform. So the location of particle P in reference frame A is equal to the location of particle P in reference frame B, plus however reference frame B has moved relative to A. All right, well I said relative velocity, and indeed we can take the derivative of this equation. If we do d by dt of the r, we're going to get the velocity. So let's do that. If we take the derivative of this, we're going to have dr p and a over dt, and then dr and p in reference frame b dt, and then we'll be taking d by dt of vba and t. And I did forget one point when I was talking about this. These transforms really only apply if the relative velocities are constant, if neither frame is accelerating. And that B is nasty. Okay. So the Galilean transform and its derivatives only apply if, not of, if both reference frames are inertial, which means not accelerating. Okay, so that actually lets us do this derivative. We'll find the velocity of p in reference frame A. It'll be equal to the velocity of p in reference frame B, plus, since we now say that there's no acceleration going on, VBA is a constant, we can pull it out in front. And we take the derivative of t with respect to t, which just gives us 1. And this tells us about the relative velocities of particle p in reference frame B versus reference frame A. And I do want to point this out. Notice it's PA, then PB, BA. Essentially, the B gets knocked out by this. It's a little bit chain rule-ish in that respect. So whatever is on the outside of the extremes inside the Galilean transform, that's what you're transforming to. You get PA, you see. Here, P and A, because PB, BA. All right, what happens if we take the derivative of this? What about the acceleration? Well, to get acceleration, we'll have to do d by dt of our velocity. And here, there's really nothing interesting going on. So VBA cannot accelerate. This is constant. So when we take the derivative, we're just going to get VPA. The particle itself can accelerate. Nothing restricts it. And dVPB dt, and then plus a whole lot of nothing because derivative of a constant. All right. There are a number of different interesting problems with this. The most interesting problems of all tend to be things where you have currents. So a fairly typical problem would be to have a river. And the river will have some speed relative to the banks. So velocity of river relative to bank would be like RVBA. And then we could have something like a person or a boat inside of this reference frame. So let's put a boat in here. And the boat can have a speed relative to the river. Let's call it a ship instead. So then I can use S with R. All right. And what we can do is start thinking about, from a perspective out here on the bank, from a stationary perspective, what would the speed of the ship be relative to us sitting on the bank? And that will depend on the speed of the ship relative to the river, which is like VPB. And this thing right here, VSB, is like VPA. Okay. Now here I've drawn it so it's all in a line, but when it really gets interesting is like when you have the boat trying to go at an angle while the water goes straight along the side. Or, like, imagine if you're trying to steer an airplane somewhere. You tend to get the speed of the airplane relative to the still air, or relative to the air that you're moving in. So the wind isn't really measured by the tools inside of an aircraft that measure speed. So if you want to steer such that you actually arrive at an airport, you have to deal with the wind, and you have to not just steer the airplane so it's going the right direction for still air, you have to still steer it, accounting for the motion of the air itself as well. So for instance, if you had airport going from A to B, and you pointed your airplane right from one to the other, so the plane relative to the air, you pointed straight at it, well, you'd better hope that there's no wind, because if there is wind, which would be the velocity of the air relative to, I'm using A too much. Wind was the better choice. You're going to have to take those two vectors together to figure out where you'd actually end up. And you can easily steer yourself off course and not go where you want to go. We will try a problem related to this in class, so make sure you're here for that. I think you'll find it useful. Maybe. There is one homework problem that relates to this, and it's more of a river problem. But maybe your quiz will end up being a relative motion problem. Probably not. It's probably going to be projectiles. But you should study both regardless. All right, I'm going to stop there after probably being confusing for the last minute. When we try problems, this will make a lot more sense. So expect this first introduction to be confusing. All right, that's going to be it for this one and for the chapter. So I'll see you in the next chapter.